So today, for Honors Algebra 2, we are going to talk about Section 6.1, Graphs of Polynomial Functions. Our objectives are going to be two. Our first objective is to describe the key features of a polynomial function. And the second objective is to identify the key features of a polynomial function from a given graph. So we're going to work on those two things. The first one we're going to talk about, and you're going to see this in the Edgenuity video, they'll give you the definition and stuff. The question is, which polynomial functions are written in standard form? So standard form, all standard form is when the highest degree, that is the highest power, is all the way on the left of the expression, and then you work your way down in powers, and you have the constant, that is the number, all the way at the end. Okay? So if you look at that, then you should see very quickly that choice A is not in what they call standard form, because for it to be in standard form, this negative x to the fifth would have to be in the front. Okay? So A is not in standard form. B, on the other hand, we've got a negative 3x to the fifth first, and that is the highest power, the highest exponent. And then the next highest is x, or x to the first. And then we have the constant at the end. And so B is a yes. That is indeed in standard form. Then when we look at C, well, x to the fifth, that's the highest exponent, is in the front, and that works, and that's exactly what we want to see. But then we've got x next, and then x to the third after that, and we actually want them to go down in order. So this one actually is not in the right order, so it is not a polynomial function in standard form. It's still a polynomial function. It's just not in what we call standard form. For it to be in standard form, the x to the third would need to be before the 2x. Okay? And finally, we've got choice D, which is has an x to the third, which is the highest exponent, and then a negative 8x to the second, and then there's nothing else. And it's okay that there's nothing else. Those are the only two things involved, and they are in the correct order. So yes, that one is in standard form as well. So I'll give you a moment to look at that and a moment to ask any questions. You can put them in the chat or unmute and ask questions now. Okay. Doesn't look like there are any questions. So if there are no questions, I'm going to move on. This question asks us to give the degree and the leading coefficient of the polynomial. So two things that we got to know here. How do you define degree? The degree of a polynomial is just the highest power. So the degree equals that highest power right there. So the degree is 5. Then the leading coefficient is the number attached to the variable that has the degree defining power. So you say, okay, this is the degree, that makes this the degree-defining term. And so you just, for the leading coefficient, you take the number that is in that degree-defining term, so the leading coefficient is -3. Okay? One thing that you should be careful of, a note here, that you need to be cautious about, is that negative and a minus sign are the same thing. So if they gave you a polynomial that was not in standard form, and they gave you something like, say, 5x squared minus 6x to the 8th, the degree-defining term is -6x to the 8th, which means your leading coefficient would be -6. Okay, I'm going to give you a moment to look at that and come up with any questions you might have. Unmute or put in the chat now. That, by the way, this ability to mix up negatives and minuses is why I always suggest to you, and will always suggest to you, to change every minus to plus negative, and then very clearly that's a -6. It helps to take the ambiguity out of it. So if there are no questions, I'm going to move on. There's a part in the lesson where it talks about using technology to graph various functions, and my go-to graphing technology is Desmos.com. Really, really good graphing technology. I highly suggest that you use it. However, I would add a bit of a caveat here. You can't use Desmos on the SAT, so you really would like to know, you really want to make sure that you know how to use a graphing calculator also. Just a little piece of information there. Okay? Any questions about Desmos or graphing calculators at the moment? Okay. I am going to move on then. All right. So now we've looked at the equations. We've looked at the function equations. Now what if we're looking at the graphs of the functions? And how can we know things about the function, especially the degree of the function? And when we say degree, we don't mean a specific number. We mean whether the degree is odd, or even, more than anything else. And then the sign of the function, that is positive or negative, whether the leading coefficient is positive or negative, and whether the degree is odd or even, whether it's 4 or 3, or might possibly, could it possibly be 2, 4, 6, 8, whatever, or would it instead have to be 1 or 3 or 5 or whatever? So you can tell these things just by looking at the picture of the graph, okay? And so I'm going to take you through the ways that you can know that, okay? if it goes like, let's look at A here. In A, on one side we're going up, on one side we're going down. And it doesn't really matter which one's up or down for the first part. The degree must be odd. That is, if you put the equation for this, if you started writing the equation for this function, your largest exponent would have to be a 3 or a 5 or a 7 or a 9. It would have to be an odd number. So the degree must be odd. And the reason for that is because the ends, or what we call the end behavior sometimes, the ends go in opposite directions. One goes up, one goes down at the end. So since one goes up and one goes down at the end, that's how we know that the degree has to be an odd number. Okay? The leading coefficient must be negative. And how do I know that? Well, here's how I know that. Because, well, let me say because first. Because the first end comes down. That is to say, it starts up here and comes down like that. So if you were tracing this and you were moving from left to right, you'd have to trace down first, and then at the end it again traces down. Okay. So the first end comes down, or that is, the first end is pointing up, however you want to think of it. So that's how I know that for A, and this is all for A. Try and isolate that. And then for B, the degree must be even, because they both go down. That is, the ends, the end behavior, both go down. And it's not really down, it's just in the same direction. Okay? If you've got opposite directions, your degree is odd. If you've got the same directions on both sides, your degree is even. And then because they're both down, the leading coefficient has to be negative. So for an even degree polynomial, if both ends point down, you've got a negative leading coefficient. If both ends point up, you've got a positive leading coefficient. I'll pause for a second and let you look at that and see if there are any questions. Okay. There being no questions at the moment, I will move on. All right, so here's another one. Give the degree and the sign of the leading coefficient, and then describe the end behavior. And that's going to get into some notation, okay? So the degree as you can see, it goes up on this side. It also goes up on this side. So because it goes up on both ends, the degree must be an even number because it has the same end behavior for both. Okay? So the degree has to be even because they both do the same thing at the end. The leading coefficient, in this one they both go up. So the leading coefficient must be a positive number. If they both go down, it must be negative. And you can actually tell just by looking at this one here. If it goes up for an even function, the leading coefficient is positive. But if it goes up for an odd degree polynomial, then the leading coefficient is negative. Okay? So just something to think about. Then we got to talk about the end behavior. And this is important because there is specific notation for it. And here's the notation. As x goes to negative infinity, that is, as you keep looking farther and farther to the left, okay? So as x goes to negative infinity, what happens? What happens to y? Y goes to positive infinity, right? Because no matter how far I go that way, this end part is just going to keep going up and up and up and up. Okay? So that's as we travel to negative infinity. And then the other end behavior question is as x goes to positive infinity. So then we're looking at this part over here. So what happens as we go farther and farther that way? Well, we go farther and farther up still. So in this one, as x goes to positive infinity, y also goes to positive infinity. And as long as you can understand the notation and figure out the notation, you should be good on this. Because it's not that difficult to figure out the actual end behavior. The toughest part is getting the notation right and understanding how to write it. I will pause for a moment to allow questions. Okay, moving on to the next slide, the next board. All right, so now there's going to be a question of where is the function doing certain things. So I've got a function graphed over here, and the question is, where is it increasing? So what that asks is, as we move from left to right, as we move in that direction, when is the function going up? Okay? And if you look, it's going up from there to there. And that's the only time it's going up, right? From here to here, from negative infinity to this turning point down here, it's going down. And from that turning point forever to the right, it's also going down. So it's increasing in one spot. And so what we would do is we always want to define these by their x values, where they fall. And this one falls between an x value of -1 and goes all the way to an x value of +1. And so we would say that it is increasing between -1 and 1. Okay, so there's the increasing. So then where is it decreasing? Well, it's decreasing in two different spots. Here, and then again here. So it's decreasing from x between, or not between, I'm sorry, not between, x less than -1. In other words, if you start at -1 and just go that way forever, it's always decreasing. It's got to come from the top and come down. It's always going down, 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 down. As you move from left to right, if you started from way back at -infinity. So it is decreasing there, and it is again decreasing from x is greater than 1. That is, we have the 1 right there, x equals 1 right there, and as we move this way, we always go down. Okay? So you always want to think of it as moving in that direction, from left to right. And then, what is the degree of the function? Is it even or is it odd? Well, if you look at it from the center, it goes in opposite directions as you move away, so that means it must be an odd degree function. I'll pause a moment for possible questions. Okay, there being no questions, I will move on to the next board. So now we're going to ask a question from the other side. If I give you this scenario, a function is a 5th degree polynomial, and I ask you how many turning points can it have? Okay, so one of the things you're going to learn is that a 5th degree, whatever degree actually that you have, means you could have it have that many x-intercepts. So I can draw a theoretical version. Now, it doesn't have to have this many x-intercepts, but it could possibly, okay? It can't have any more than this. It could have less. But 5th degree means it could have 5 x-intercepts. So I'm just going to mark 5 x-intercepts. So we'll do 1, 2, 3, 4, and 5 x-intercepts. And then I'm going to draw a graph to where I hit all those x-intercepts. And I'm just going to keep crossing the x-axis. So up and down, up and down, up and down. And then after I cross my last x-intercept, it'll go either up or down forever. I could have done this in the exact opposite way, right? And then I just want to look at the turning points. That is where it goes from going up to going down, or going down to going up. So here's one, here's one, here's one, here's one. And that's the most that I could have. It's not the only number that I could have because of weird things that can happen, but it is definitely the most that I could have. So at most, there are 1, 2, 3, 4 turning points. That's at most. There could be less, but there cannot be more. So at most, there are 4 turning points. So I will pause for a moment, allow you to look at this, see if there are any questions. Okay. There being no questions, I will move on to the next board. And now we've got some statements, and I want to know which statements are true of these three statements. And you're going to learn about local max and local min. So the first two statements are about that. So the first one says the local max and min always occur at a turning point. And so what a local max is, let's say we have something like this, okay? A local max would be as high as you can go. So here's one, and here's another one. So those are local maxes. And a local min is as low as you can go. So there's a local min. And I think just by looking at the picture and hearing that explanation, I hope that you can see that indeed this is true. The only place local max and mins occur is at turning points, right? Otherwise, you don't have local max and local min. Here's a local max. Here's a local max. They only happen because you start turning down, right? Here's a local min. It only happens because you start turning up. So the turning points are actually what helps define the local extrema, they call it, the local max and local min. So indeed, this one is true. Let's look at what B says. The local max is the x value of the coordinate at that point. So going back to our little drawing here in the corner, this is a question of how do we name it. If I ask you what is the local max at, would you talk about the x value or would you talk about the y value for this point? And so here's the thing. If you talk about the x value, then I don't know how high that local max is. I just know where it is along the x-axis. But if I use the y value, then I know how high it is, or in the case of a local min, how low it is, right? So it is the case that we really do want to talk about the y value, how high it is or how low it is, more than anything else. So this one is not true. And finally, let's look at C. The ends of an even degree polynomial either both approach positive infinity or both approach negative infinity. Well, let's look excuse me, at an even degree positive or an even degree polynomial. Let's say something like that. There's an even degree polynomial right there. Well, in this case, the end behavior, the ends of it, both go up, meaning they're both going to positive infinity. If I had drawn it the other way, like this one here, which is also an even degree polynomial, they both go down forever and approach negative infinity. So indeed, this one as well is true. I'll pause for a moment in case there are questions. Okay. There being no questions, I will move on to the next and last board. So, our last question. Which of the following terms, when added to the given polynomial, will change the end behavior? So now end behavior is based on two things, right? It is based on whether it's odd or even and whether it's positive or negative. So which of these things would maybe change the degree of the polynomial, which would, right now, as you can see, the degree is 7, so it is an odd polynomial, meaning one side goes up, one side goes down in one way or the other. So certainly, if we put this this negative x to the 8th in there, then that would become the degree-defining term, and so that would change it to an even degree polynomial, and change it to either both of them up or both of them down. B wouldn't change anything about the degree. And if you don't change the degree, you can't change anything about it. You can't change the leading coefficient, which tells you whether you start up or down, that sort of thing. So B we can ignore. Now C. What if I added in C? Let's take a look. What if I did negative 2x to the 7th plus 5x to the 7th, and then if I had the other stuff in there too, I'll write the other stuff. But all I really need to focus on is these two, right? When I added those two together, I would do negative 2x to the 7th plus 5x to the 7th is positive 3x to the 7th. And then all of a sudden, that degree-defining term has gone from a negative to a positive, and because of that, I changed the end behavior, right? Instead of starting going down, now it starts going up. So C definitely changes things. Now D and E, all they do is change the constant at the end. That has nothing to do with the degree-defining term, so they don't have anything to do with it. All right. That is the last board for this section, and we will see you in future sections.